recently, but we used to do this as kids. Alphabet soup, you start looking for, kids are looking for words, right? Or they try to spell their name or something in alphabet soup. And if you just pour this randomly at random, there's going to be words, and we're perfectly happy to attribute those to coincidence, right? So 3-letter word, there'll be short words. They're messy. It's C. It's a short word, but it's kind of a messy version of C. So you're not at all spooked by seeing that. It's not like, oh my goodness, a message from God. C in my alphabet soup. May, again, it's messy. The A's upside down, short words. There's a 4-letter word, but it's even more messy, right? Rose, you have to kind of curve it around. Coincidence. We're very happy to attribute these to coincidence. When I gave this talk, someone pointed out holy. Do you see holy under C there? H-O-L-Y. Now that is no coincidence. No, that is a coincidence. But if you were to lift the lid on a pot of alphabet soup and see this, you would know that is not a coincidence, okay? So, and a 4-year-old would know this. So what I want to ask here is, we all get this. Is it possible to actually show, could you bring a team of scientists in here and say, yeah, you know, not only do we all know this, but we can prove that the 4-year-old's right. That can't happen by coincidence. Is there a way to do that? And there is. You use the math of probability. There's a very simple sort of analysis you do. So for this, I would put a grid of squares over the picture, and the grid squares are about the size of the letters in this alphabet soup, and there's 23 grid squares, and there's something somewhat special about all 23 squares. In 5 of them, you have the 5 letters that spell pasta. In the other, 18, you have these relatively cleared zones that make the pasta letters, the pasta word pop, right? They pop because there's a clearing, and then you get the 5 letters in there. So there's something special going on in all 23 of these squares. And we could just, with a rough calculation, ask ourselves, how special is what's happening in those 23 squares relative to the rest of the alphabet soup surface? And it turns out, if we say those 18 squares that are cleared are like 1 in 10 unusual, and all we're saying there is you'd have to look at quite a big region of this random soup to find a cleared spot, at least 1 in 10, but we'll just use 1 in 10. And the 5 that have the letters that spell pasta are like 1 in 100 unusual, because they have not only a letter in them, but the letter is oriented the correct way. It's not upside down, it's right way up. And the letters spell a word, so it's somewhat special. We'll call it 1 in 100 special. If that's true, if these numbers are, and they don't have to be exactly right, the whole pattern is 1 in 10 to the 18th, and that's for the 1 in 10 special for the 18 cleared squares, times 100 to the 5th unusual. The 1 in 100 is for the letter squares. And if you multiply that out, it's 1 in 10 octillion unusual. So this simple calculation, and a scientist would say, yeah, that's about right. You would need to pour 10 octillion bowls of alphabet soup in order for something like that to come out just by coincidence. And you will never, God help us, you will never pour 10 octillion bowls of alphabet. If all the oceans were alphabet soup, it would not give you 10 octillion bowls of alphabet soup.